Hi, I'm John Simon, and welcome to my tutorial on the aerodynamic aerosol classifier. You join me today on a wet day in October in Cambridge, England at the Cambustion HQ. So while I go to the lab and set things up, I'll leave you with some PowerPoint slides explaining what the AAC is. See you later. The aerodynamic aerosol classifier, or AAC, solves two problems in aerosol science. The first is, how do I select a monodisperse size classified aerosol without multiple charging or zero charging artifacts, as you may get with the DMA? The second is, how do I select monodisperse aerosol based upon aerodynamic diameter, if that's my metric of choice? The most common monodisperse classifier is the Differential Mobility Analyzer, or DMA, with which I'm sure you're all familiar. This uses electrical mobility classification, which is the motion of charged particles in an electrostatic field. This is related to the number of charges on the particle and the drag of the particle, which in turn is a function of its size and shape. This suffers from multiple charging artifacts. Smaller particles with one charge may end up having the same electrical mobility as a larger particle with two charges. Because there is less chance of smaller particles being charged in the radioactive source of the DMA, this means it is inefficient at transmitting small particles. Uncertainty is introduced due to these artifacts. Now, in an SMPS, correction can be applied during the inversion algorithm, but the uncertainty cannot be eliminated. And when using a DMA to select particles for online analysis, large particles with more than one elementary charge can degrade performance or skew results. What of course you want when selecting aerosol with a DMA is just one peak. What in fact you might get on the right is multiple peaks depending on the underlying size distribution from which you're selecting, and these may have one charge, two charge, or three or more charges at progressively larger sizes. With the AAC, you just get one peak with a high transmission efficiency even for smaller particles. As I said at the beginning, the AAC classifies by aerodynamic diameter. Aerodynamic diameter is best explained by the use of an impactor. Particles accelerate through a nozzle region, and the largest particles, unable to follow the gas streamlines due to their inertia, are impacted on a plate, whilst the particles with the smallest aerodynamic diameters follow the streamlines and emerge. The diagram on the right shows an impactor in front of a common DMA, which is used to remove the larger particles before classification. The aerodynamic diameter of an irregular particle is defined as the diameter of a spherical particle with a density of 1,000 kilograms per cubic meter and the same settling velocity as the irregular particle. Aerodynamic diameter is the size metric of choice for many aerosol scientists, especially those working in inhalation, health effects, and filtration. Rather than just determining the size of particles in an aerosol stream, it's often desirable to be able to classify them online for further analysis. The state of the art at the moment is an impactor, which is effectively a low-pass filter. It allows through the smaller particles. If you want to allow through the larger particles, you can get a virtual impactor. The AAC allows a band pass by aerodynamic diameter, i.e. particles over a finite size range, to be selected. So how does the AAC work? Well, like a DMA, there's a sheath flow in a classifier, but unlike a DMA, the classifier is spinning, producing a centrifugal force, and there is no electrical field. Smaller particles are lost to the sheath flow. Larger particles land on the inside of the outer cylinder of the classifier. And by setting the speed to be just right for the aerosol particles that you desire to leave the classifier, those particles emerge through a narrow slit from the right-hand side of the classifier as a monodisperse aerosol. So in this first practical part of the tutorial, I'm going to be creating a monodisperse aerosol for the AAC. So I'm going to be using DOS, which is this oil here, and I'm going to be nebulizing it with a Colson nebulizer, catching any large drops, then classifying with the AAC by aerodynamic diameter. The aerosol will then come out through this aerosol flow meter. That's an optional accessory for the AAC that will move the flow. We're going to add some make-up air through this HEPA filter and valve, and then we're going to go into the DMS 500. Now the DMS 500, as you'll know, is the world's fastest electrical mobility spectrometer, and I'm using that today rather than SMPS for speed, so we don't have to wait for the scans to build up. This will show the monodisperse output from the AAC. So I'm going to turn the nebulizer on by connecting the air, and then I'm going to set up the AAC. So because the AAC classifies by aerodynamic diameter and the DMS measures by mobility diameter, I'm going to enter a density into the AAC software, which will allow the AAC to do a conversion between those two metrics. So if I go into Setup, and then I'm on the aerosol tab, I'm going to enter the density of 914 kilograms per cubic meter for the DMS aerosol, and that means the AAC will do the conversion for us. So we've got a sample flow that's being measured by the aerosol flow meter of getting on for a litre a minute there. The AAC, if I enter a resolution, and the resolution is the ratio between the width of the distribution and the set point of the distribution, so this means that the distribution is 1/10 of the centre set point in aerodynamic terms. It will then regulate the sheath flow to give me that resolution, because like a DMA, the resolution in AAC is the ratio between the sheath flow to the sample flow. And then I enter a size, so I'm going to enter 200 nanometers to start with. I'm going to enter 200 nanometers, and then I'm going to actually convert it to aerodynamic diameter. So it's done the conversion, it goes to 188 nanometers in aerodynamic diameter, and then I'm going to start the AAC. So meanwhile, the DMS is showing the broad aerosol coming out of the nebulizer. As the AAC starts up, it'll start to classify the aerosol. We should see distribution coming in from the right, because as the AAC speeds up, it classifies smaller and smaller particles. Now the DMS has two data inversions, as you may know. It has a 45 class spectrum, which is shown in red there. It also has a log normal fit, which is much higher resolution than normal spectrum, and that's shown in yellow. And that's showing more the true narrow distribution that's coming out of the AAC. On the screen. Okay, there we are, 200 nanometers. So if I change the set point on the AAC to 100 nanometers, and to 100, and then the convert to aerodynamic diameter, which comes out at 93 nanometers in aerodynamic diameter. The AAC speeds up to match that set point. Because the peak of the underlying DOS distribution is much larger than where we've set the AAC set point to, the concentration comes down slightly. Now, the take-home message here is there is just one peak. If you're using a DMA for this experiment, particularly at these large sizes, you'd see multiple peaks from multiple charging states of the particle. So the AAC is a very useful tool if you just want to select particles by size and you just want one peak. You don't need to worry about multiple charge because there's no charging involved in the AAC classification process. It's a sheet flow in a centrifugal force. There we are, 100 nanometers. And that concludes the first part of this tutorial.
The AAC can be combined with a variety of condensation particle counters used downstream of the classifier in order to build up a size spectrum of an aerosol. There are two scanning modes available. In the step scanning mode, the AAC changes speed, waits for stability, then takes a CPC reading and repeats for other sizes. This is quite a slow scanning mode. In the continuous scanning mode, which was developed last year, the AAC constantly changes speed and the CPC constantly takes readings, and data is corrected for the lag. This is like a scanning mobility particle sizer equivalent. This is faster and has higher resolution. The electrical low pressure impactor, or LP, is an established instrument for determining a size spectrum according to aerodynamic diameter. Here we have an LP spectrum in blue and we have AAC spectra in orange and grey, and we show good agreement between these two different types of instruments.
Also, by converting the aerodynamic diameter to mobility diameter, we can compare with the scanning mobility particle sizer. And here again, we show good agreement, although the SMPS is limited to sizes much smaller than the AAC can go to. As I said, in 2019, we developed continuous scanning, or ramping scanning, which reduces the scan times considerably and increases the resolution. Here's an example of some results from that. So this is the aerosol lab at Combustion in Cambridge. The scans start at 18:20 in the evening when people start to go home, and by 20 to 10 in the evening, you can see that the concentration has reduced in time as we take continuous scans over that period. Okay, in the second part of this tutorial, I'm going to be doing a scan with the AAC, and I'm going to be using this bottle of PSL spheres, which is 600 nanometers. I'm going to be putting a drop of these in this ultrasonic nebulizer, and then I'm going to dry the aerosol using this silica gel, this diffusion dryer. I'm then going to put it into the AAC in scanning mode, which is connected to this CPC, and build up a scan showing the peak of the distribution. A couple of things I need to do to start with on the AAC. First thing, I need to tell it to use this particular CPC. So if I go into Setup, CPC, and then I'm going to select this particular CPC. You can see there's a range of CPCs you can use from a range of manufacturers. This one happens to be a TSI 3775. So I'm going to put in that. I'm going to match the flow to the CPC in high flow mode. I'm then going to set the density of the aerosol. Now this is PSL, which has a density of 1050 kilograms per cubic meter, and this is just to make sure that the mobility diameter conversion, which also happens in the scan file, is right, and that will enable us better to compare with what's written on the bottle of PSL. And then I'm going to go into scan mode. So I'm going to set up scan. I have a memory stick in the side here to record the scan. My file name I'm going to call 600 PSL. Sheath flow is going to be set to 15, which will give a resolution of 10. I'm going to scan from 500 nanometers to 800 nanometers to catch the peak. This factor here shows you the spectral resolution. This is the total time of the scan and any extra delay time depending on the length of tube you're using to the CPC. And I'm going to do one scan. Okay, so I'm going to start the nebulizer. I've already put a drop of PSL in there. Okay, so if I press start, the AAC starts, and you can see we're reaching the start of the scan here. So we've got to get to 157 radians per second, which is about 1500 RPM. The scan starts. I'll also set the sheath flow. And a spectrum should start to build up from the right-hand side, which is the larger particles. So this countdown shows the total scan time, building up to 60 seconds. On the right-hand side, we're building up towards the peak of the PSL distribution. Okay, you can see summary statistics at the top here. So the peak is around 620 nanometers, and you'd expect for that particular density in 600 nanometers in mobility space for it to come out around 616 nanometers, so we're pretty close there. You can zoom in on the screen here by dragging your finger to show the spectrum in more detail. So that is a scan of the PSL peak.
And that concludes the second part of this tutorial.
So the data file of the PSL scan I've just recorded is just a plain tab delimited text file. It doesn't need exporting into any other format before you can use it. I've chosen here to use Microsoft Excel, but you can use any data handling package you like, such as Igor, Scilab or MATLAB. The top of the file is a header pertaining to the particular instrument, and then there's information about the particular scan we've just taken. Below that, there's one line per size point in the file. This column here is the aerodynamic diameter in nanometers. Next to it is the size spectral density, or dNd log dA, effectively the concentration in differential form. And next to that is a version of dNd log dA that's been corrected for diffusion loss. Then we have some columns pertaining to relaxation time, which is a parameter which is related to aerodynamic diameter. And then we have columns which are in mobility diameter space. And these will be converted using the density and mass mobility exponent, which can be entered into the software. So if we want to plot aerodynamic diameter, we can just highlight that, insert a scatter plot. Convention dictates that we make it a logarithmic scale. And there we are, aerodynamic diameter. At the bottom of the file, there are statistics pertaining to the file. So in terms of aerodynamic diameter, mobility, and relaxation time. If you look right at the bottom here at the mode, the peak in the file in terms of mobility diameter, you'll see it's 605 nanometers. And if you remember, the PSL was 600 nanometers. So indeed, that's a very good result. Example applications of the AAC include filter and mask evaluation, inhalation studies, determination of the density of aerosols, optical particle counter calibration, condensation particle counter calibration, aerosol mass spectrometer calibration, particle charge determination, and selection by morphology or shape. Welcome to the final part of this tutorial on the AAC. In this part, I'm going to show you how to clean the AAC. So as with the DMA, eventually the particles which you don't require, which you don't want to be classified, end up on the inside of the AAC, in this case the larger particles, and they have to be cleaned out after a while. Now, unlike a DMA, there are no electrical components inside the actual classifier, so you don't get short circuits. But eventually you will want to clean the inside of the classifier. So this is how you do it. Okay, the first thing to do is to go up to the setup screen and unlock the lid. The AAC goes to sleep and we switch it off. We then undo the 6 clasps which hold the lid on. So, remove the lid, set that to one side. Okay, we now need to remove the classifier in order to clean it. So, we have to loosen the belt, which will make life easier when you put it back on. I like to just mark where the belt tensioner is with the Sharpie, so I can set it back later on. And then we simply release tension in the belt like so. We then remove these bolts. So 4 of those. And disconnect the sheath thermocouple. The belt we just remove from the sprockets out of the way, and then we can slide the classifier out on this side of the AAC. Okay, so I've set the classifier down safely on this piece of foam on the table. So I'm now going to take out the 6 bolts which hold the classifier together using this M3 ball driver. And I'm just going to ease the inside of the classifier from the outer. Now, sometimes this does need a little bit of force, but then we've got the inner separated from the outer. Okay, now bear in mind there are no electrical fields in this. We don't have to be quite so precious about this classifier as we would if it were a DMA. I'm just going to use this cloth to wipe, which is mostly going to be DOS oil, I would imagine, from the last experiments we did. In the classifier, you can use a little alcohol if you want, a little IPA, as you would with a DMA. Okay. Screws underneath it, set it out, and the same with the outer. I'm going to wipe down the inside of the outer. So we'll use a little IPA on this. There's a lot of oil on it. Okay, should do. And then we have to put this back into there, very obviously. So there's a hole here and a dowel here which need to be aligned. Take the classifier. Okay. Look for that dowel. We line it in that hole there. Okay. And then we can just set it up on its end. Mostly use gravity. Just a little bit of pressure, make it go home. And then we just need to put the 6 bolts back in. As is always good practice when taking anything part of this nature, from AACs to car wheels. We'll put them in loosely to start with, and then we'll tighten them progressively. Okay, just go around again. Okay, and then we can put the classifier back in. So, as we did before, on this side, get to this side, we may just need to lift it to get it over the pillow block. Okay, make sure the belt isn't caught up anywhere. Good. Just slide it over there. We then put back in the large bolts which hold the classifier in. Usual one is rolled underneath the AAC. Those. And we reconnect the thermocouple on this side, pushing the connector back on, and then we just need to put the belt back on. So guide the belt over the idlers and just push this back to where the mark was set before, approximately. It's not critical. You've done this a few times, you get used to how tight the belt should be. Okay, that's back in. We can then put the lid back on. the guides at the back. Do up the over-centre clips. And then we can switch the AAC back on. Okay, when you switch the AAC back on, you'll see it's come up in safe mode, and this means that it will run through 1 minute of limited speed just to check that everything's been put back on properly. So if I press run, it wakes up. Locks the door. And runs through 60 seconds of limited speed running. At the end of that period, it will go up to whatever speed it was set to previously, and you're good to go. And that concludes this final practical part of the tutorial. If you'd like to know more about the AAC, please visit our website at www.cambustion.com/AAC. If you have any further questions, then please do contact me as shown on screen. At the bottom of the screen are some references on the AAC. You'll find more on our website. Thanks for listening.